Yeah. We're going to talk a lot about driving today. So congrats on passing your driving test. We're going to talk about driving today and why Newton's laws are important when you're riding in a car. Okay, so if you already don't wear your seatbelt in your car, you will by the end of today, hopefully. So this question is asking, how likely are you to wear your seatbelt in the back seat of your car? You always wear it most of the time, sometimes with the seatbelt. So you're answering this poll link is in Google Classroom. Does anyone know anything about the seatbelt laws? They do ask you questions about it on your permit test. Does anyone know anything? Go ahead.
If you're driving and you're under the age of 18, you're reliable for everyone if they're under the age of 18. But if your passengers are over the age of 18, it's their fault.
Wow, nice. Zoe? Okay. So basically, if you are driving a car and someone is under 18 in your car and they're not wearing a seatbelt, you are legally liable for what happens to them. If they're over 18, it's their own decision. But if you are driving, if you're doing your driver's test and the person who's evaluating you isn't wearing a seatbelt and you don't tell them to put on their seatbelt, that actually can be one way that you fail the driver's test. It happens to people. So you have to be wearing a seatbelt inside of a car. That law became a law in 1968. It started out in New York. And the reason being is the CDC, Center for Disease Control, determined that one of the top 5 leading causes of death in the 50s and 60s was actually car accidents. So car accidents killed more people than any other type of actual illness. So because of that, they came up with seatbelt laws to force people to wear seatbelts. We're going to talk about why it's so important to wear your seatbelt no matter where you're located in the car. We'll take this poll again towards the end of class and see how your answers have changed. Okay, so we have 50% for always, 38% for most of the time, 13% for sometimes. Okay. So this is where most people, if you survey the general population, this is actually where most people would answer, is most of the time. You guys are a little bit better than the general population. So about 50% of us said always. Okay, so we're going to talk more about why wearing a seatbelt is so important after our little lab activity today. So the reason why it doesn't matter where you're located in your car is the amount of force acting on you is the same. We'll talk about first what a force is, and then how forces kind of work in the case of a car. So a force, I like to think of this as how you open or close a door. Depending on what kind of door it is. Okay, so how you open or close a door, you apply force to it. What is the force? What do you physically do to open a door? Push it. Push it. Okay, or if it's a pull door, you want to pull it. Depends on what kind of door it is. So a force is either a push or a pull. And why do we apply forces? Go ahead.
To put movement into an object?
To cause movement, exactly. So the purpose of a force is to cause movement or to stop movement. Okay, and what we do with that force, we push or pull. So a force is a push or pull upon an object resulting from the object's interaction with another object. So for example, you push door. That's a force. There has to be 2 objects, you and the door. You apply force to the door, that door applies a force back on you. If you're pushing it, it's technically pushing back on you. Okay, or you can pull a door, that's also applying a force. You pull a door, it's applying a force. But there must be 2 objects. Forces occur in pairs. There has to be more than 1 object. Okay, force, just like acceleration, just like velocity from our last unit, force is a vector quantity. What does that mean? What's a vector quantity? Zoe?
Has a direction.
It has a direction. So it's a vector quantity. Direction matters. So which direction you apply that force determines which way it's going to move. Right? So the direction of the force matters. It's a vector quantity. This symbol that we use for force is usually a capital F. That's the variable that we use. Does anyone know what units we measure force in the US?
Pounds?
Pounds, yeah. So in the US, we measure forces in pounds. In the UK, we use newtons. So force is a measurement of newtons, named after this guy called Isaac Newton, who we'll talk a little bit more about. But the units are newtons, which we use a capital N to represent. So the units are newtons. A newton, the definition of a newton, it's technically a kilogram times a meter over a second squared. Physicists are into efficiency. That's a lot to write from line to line, kilogram times meter over second squared. So they simplified that to a newton, capital N, named after the guy who invented or defined what a force was for the first time. And newtons is the same or similar to a pound. So if we convert from metric to English system, there are 4.45 newtons in every pound of force. So this is what we would use. Engineers in the US would use pounds, pounds per square inch, PSI. So we usually measure force in. Okay, basically everywhere else in the world we use 4.45, we use newtons. But we can convert from time to time. Okay. So let's talk about who Newton is. Anyone know anything about Isaac Newton already? Isabella?
He was sitting under the apple tree and the apple fell. And he was like, gravity, right?
Yeah.
He made like the laws, the 3 laws.
The 3
There's
laws.
probably more, but 3.
There are actually only 3. You're right. There are only 3. So this is a story, we're not sure how real it is, but he was sitting underneath an apple tree and an apple hit him in the head and he thought of the idea of gravity. So I'm going to watch a quick little bio clip about who Newton is. So if you think back to Galileo, right, he was a rich son of a musician in Italy. So he got away with a lot of things. Newton is actually the son of a farmer. His parents were disappointed in him because he wasn't a good farmer. He went to Cambridge instead. In order to make it at Cambridge, he had to clean other people's dorm rooms and waitress or waiter in order to pay to go to school. And what's pretty amazing is that during a pandemic, that's when he thought of the 3 laws of physics. So he was isolated by himself at home during a plague, and he had basically created he wrote down the 3 laws that unify how everything in the universe acts. Everything in the universe, 3 laws. Okay, so watch a quick little video of Isaac Newton. We call him the father of physics because he basically defined what physics was in a textbook at 21 years old.
Revolutionary English physicist, mathematician, and philosopher Sir Isaac Newton is perhaps the most famous scientist in history. Born to a farmer in 1642, Newton worked his way through school waiting tables and cleaning wealthier students' rooms. He went to university at Cambridge, where he would eventually earn a professorship. During the Great Plague in 1665, Cambridge shut down and Newton returned home. It was during this hiatus that he first conceived the method of infinitesimal calculus, began to theorize the laws of planetary motion, and started his work with light and color.
Okay, so on a break from school after his freshman year of college, he invented calculus.
How do you just invent calculus?
Right. So basically he was doing experiments on why objects move, and the math that he wanted to model, it wasn't specific enough. So he literally invented a operation in math in order to understand what was happening in his observations and his experiments. He was so humble though that he wrote down all this information. At the same time, someone else was also studying and trying to invent calculus. Because he was so humble and didn't actually tell anyone about basically the book he wrote until years later, there's this feud that in the math community that another person invented calculus, but his book was written first, so he technically invented it first. But because he was too humble, didn't show anybody, someone else almost got credit for it.
Wait, who would you bring this to?
That's a great question. So exactly, nobody. Who would he bring it to, right? He's at home from school on break. He writes this book that basically invents calculus so he can study planetary motion. Then he goes back to school. It's like, who are you going to show this to? Your professor, right?
Like, they don't know what it is.
Right. Also, he was probably afraid that people would think he was nuts, right? So he had to become a professor and kind of be acclaimed in the community before he could be like, hey, I wrote this book. And then once he published the book on calculus, then that's where his 3 laws came from.
Though his discoveries would change the world of science, he didn't care about the glory and fame that came with them.
He wasn't too concerned with publishing it, making it available to other people, getting glory in his own sake. It was an intellectual challenge that he wanted to deal with.
Every discovery that Newton made had 2 aspects. First, Newton made the discovery, and second, other people had to discover that he had made the discovery.
In 1671, Newton demonstrated his revolutionary reflecting telescope for the Royal Society, and soon after published his notes on color, describing his research on optics. After a visit from Royal Society member Edmund Halley, encouraging Newton to prove Robert Hooke's hypothesis on planetary motion, Newton wrote his Principia, which introduced his 3 laws of motion and first described the idea of gravity.
Okay, so basically, Halley's Comet, have you guys heard of that before? The scientist that comet is named after basically went to Newton as a favor and said, I need you to prove Robert Hooke's hypothesis was correct using what you know about math. And because of that favor he was doing for a friend, that's where his book that defines physics came from. 3 laws that unify how all forces work in the universe. So as a favor to a friend, he began researching, and then from that became the book, which they'll talk about. Your bio teacher will tell you that Darwin's Origin of Species is the most important book to science, but if you're talked to a physicist or a mathematician, this book is the most important foundation of science. That's why we call him the father of physics.
Newton's Principia is generally reckoned to be the single most important scientific book ever written, because for the first time it set forth a working, quantitative, exact, mathematical system based upon experiment and critical observation.
His work made him very popular and led Newton to being elected to Parliament. After several years in London, Newton suffered a nervous breakdown. Though he came out of it, his interest in physical science was replaced with philosophy and alchemy, particularly how they both related to a higher power.
Alchemy was concerned with manipulating what were seen to be 4 elemental properties in nature, the 4 elements, earth, air, fire, and water, and realizing that these things made all substances, that we would therefore not only make any other substance, such as gold, but we would also somehow learn the secrets by which God had put the world together.
Newton's later years were spent less in science and more as a public figure. Upon Robert Hooke's death in 1703, Newton became president of the Royal Society, though he didn't get along with many of its members, and made many enemies. Newton spent his final years a wealthy and famous man, whose discoveries made enormous impact on society.
In the century that came after, the 1800s, we find that the fascination with science, with order, and with reasoned knowledge really set the whole tone of that culture. The one single figure from whom they drew most deeply was, in fact, Isaac Newton.
Okay, so his book, for the first time, kind of set out a blueprint of how we experiment in science. So it not only defined the three laws of physics, but explained how we experiment. And from those experiments, basically a period of great enlightenment came. So most of the stuff that we know about science occurred because of Isaac Newton. We call him the father of physics. Okay, so he founded the science of physics. That's what he's most known for. And calculus, but he founded the science of physics. Biological Principles of Natural Philosophy is the name of his book. He wrote in Latin, though, so it's been translated. So we're going to talk about what his three laws are in their most basic form. Okay, it's pretty amazing that he was able to, we go to outer space, and we'll show a video of outer space in a few minutes. We go to outer space and test out his predictions. He was actually right, even though no one in his lifetime had traveled to outer space. So being able to make those predictions is pretty fascinating. We're talking about his three laws. You probably learned about maybe the first law before, or maybe all three in 8th grade. Does anyone know what his first law is? Isabel?
An object in motion will stay in motion unless acted upon by an outside force.
Yes. Okay, so we'll get back to that in a second. But objects in motion stay in motion, objects at rest stay at rest. So basically, his first law explains why objects want to maintain the type of motion they have. Another nickname for this law is the law of inertia. Inertia is a tendency of an object to resist changes in motion. Basically, objects want to maintain whatever motion they have. So inertia, objects' natural tendency to resist changes in motion. So this idea of inertia relies on some property of an object. So if we're talking about me versus the earth, if you apply force to me versus applying force to the earth, which one's more likely to move? Me. Why?
If you're a smaller mass.
I'm a smaller mass, exactly. That's what inertia is. Inertia is a measurement of mass. So inertia is proportional to mass. The more massive an object is, the harder it is to get it to start moving or to stop it from moving. So you have more inertia if you have more mass. Okay, this is a review from chemistry. Do we know what mass is? Jackson?
Is it how much is gravity acting upon you?
That's weight.
Ah.
Close. Go ahead.
How much space you take up?
That's volume.
Oh.
You're on the right track. We almost got it, guys. Go ahead.
Like how much is inside an object?
Okay. Basically, how many molecules are inside of an object? How many atoms it's made of? Exactly. So mass is a measurement of inertia. It's measured in kilograms. It's the amount of matter something has. How much matter that object is comprised of. So what type of atoms and how many? And it's measured in kilograms. Weight is measured in newtons. Weight and mass are different. We'll come back to that in our next class. But mass determines inertia. Also, if objects will move or not when they're pushed. Okay, and this idea of inertia, how massive an object is, that is where Newton's first law came from, which Isabella told us before. We're just going to add a little bit to it. There's only one distinction from the definition you learned in 8th grade. So an object at rest remains at rest. And an object in motion remains in motion with constant velocity. Unless it is acted upon by an outside force. Other words for outside that you might see: net force, unbalanced force. So objects at rest stay at rest, objects in motion stay in motion with a constant velocity, unless it is acted upon by some other force. So in terms of equations, what that means. So if acceleration is 0, that's what this law explains. When objects aren't accelerating, this is what happens. The object is either at rest and it remains at rest. So velocity is 0 and it stays 0. Or the velocity is 5 meters per second and it stays 5 meters per second. So this first law explains when acceleration is 0, objects either maintain no motion or they move at a constant velocity. Okay, and why that happens is because when you add up all the forces, when you sum, that's what that symbol means, summation. When you sum, you add up all the forces, they will equal out to 0. So when you add up all the forces acting on the object, forces are vectors, you'll get a big fat 0 as a result. There's no net force, there's no acceleration. This is a little bit harder for us to imagine and picture because, for example, my roll of tape. Why does my roll of tape come to rest? So I applied a force to it that you can see. Why does it come to rest? Go ahead.
Friction's acting on it.
Friction's acting on it. So on Earth, it's a lot harder to see this moving at a constant velocity thing because we have air resistance, we have friction, and we have force of gravity. If you wet a washcloth, you fill it with water on Earth, and I wring this out, what's going to happen?
Water's gonna pour out
Water is going to pour out in which direction?
downwards.
Down. Why?
Gravity.
Gravity, right? So if you're in outer space where there's no gravity, there's no friction, objects move in a straight line forever, which is terrifying. But it's harder to see that constant velocity thing here on Earth because we have friction, air resistance, and force of gravity, which we can't physically see those things. So we're gonna watch a quick clip. We do the same experiment up in space. Let's see what happens.
Number 2, students from the
Okay, so we're on the International Space Station. We have an astronaut here who's technically accelerating. He's orbiting around Earth, but far enough away from Earth that force of gravity doesn't affect him to the same degree that it would affect us. So let's see what happens.
Nova Scotia asked Chris Hadfield to wring out water from a cloth. The results are unexpectedly quite interesting.
We might have the coolest washcloths ever here on the space station. I can show you. Here's one of our washcloths. And it's packed. It's put down into this little tiny hockey puck so that it saves some space. When you open up a hockey puck, so when you open up your hockey puck and turn it into a washcloth, it's compressed in a great big place. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what'll happen when we're doing it. Eric and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I fill the water bag. This is drinking water. to squirt a bunch of water into this washcloth.
Right, water doesn't fall in space because there's no force of gravity. Imagine how hard it would be to shower. It'd be terrible.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start bringing it in. It's really wet.
So you can kind of see what happens to the water. What's happening to the water? Jackson?
It's being pushed to the surface of the washcloth.
It's being pushed to the surface of the washcloth. So we're applying force to wring it out. So it's being pushed to the outside of the washcloth. But it's just sitting there. It's staying there. Why?
Gravity.
There is no gravity to pull it down. There is no outside force acting on it. So an object at rest is going to want to stay at rest. The water is just going to be levitating on the outside of that washcloth because there is no force to bring it down. Okay, so in space, objects they act a little bit differently because we don't have air resistance, friction, and force of gravity. That's why you see in those movies, astronauts are tied to the spaceship when they leave. It's because if they are hit the wrong way and they're not tied to the spaceship, they're going to move out in a straight line forever because there's no outside forces acting on them. But friction, no air resistance. Okay. A quick checkpoint before we start the lab. So considering what we just talked about, I got a little too excited here and sort of gave you this answer, but concept question number 1, if a spaceship is in deep space and turns off its engine, what's going to happen? This is a multiple choice question. So take a second, read the answer choices and choose A, B, C, or D. Is that a bathroom?
No.
Are you going to answer the question? All right, go ahead, Jackson.
Move with a constant velocity.
It's going to move with a constant velocity in a straight line because there's no outside forces acting on it. Good. B. All right, what about this next one? So, according to Newton's first law, why should you wear a seatbelt? Isabella?
Like, if the car stops suddenly, you'll go out the front, or if it gets hit from the side, like, you'll get.
Okay. So when you're inside a car, you are moving at the same velocity as a car. Right? You are moving at the same velocity as the car, unless an outside force or an unbalanced force stops you, acts on you. Right? So you want that force to be a seatbelt and not the windshield and then the force of gravity bringing you back down towards the asphalt and then the friction on the asphalt, because that would be terrible, right? So you want that force to stop your motion to be a seatbelt, because you are moving at the same velocity. You're going to continue to move at that velocity until an outside force acts on you. No matter where you're located in the car. Okay, and then this one's a little trickier. So if you're being chased by a giant moose, how would you use Newton's first law to get away from it? Ooh, just a cover. Okay. So you're being charged at by a moose. How would you escape that? What's different about you and a moose? Turn to someone in your area and talk about it. Using Newton's first law, how do you escape the moose?
Yeah. Well, they can lose it how to.
Stop.
Get to hit the tree.
Turn.
Yeah.
Really quiet over here, guys. Talk to each other. You guys know each other's names, right? Jenna, Chris, Emily, Ryan, you got it? When I was first student teaching, I worked in a school with like 2,000 kids, and it was January, and kids on the opposite side of the room didn't know each other's names. It was like, I was shocked, but you know each other's names, right? Talk to each other. All right, so what's different about you and a moose?
This is very large.
Okay, more massive.
Force acting on it.
One more time, Jackson.
There's more force acting on it and it's larger.
Okay, so it's larger, it has more inertia, it's going to be harder for it to change its motion. So you need more force to change its motion. So what could you do? You are less massive. You have less inertia. This guy has more inertia. Go ahead, Jackson.
You'd like turn out of the way because it'd be harder for it to turn.
You want to like sharply turn, quickly change your direction, zigzag, because it's going to be harder for the moose to change its motion because it has more mass, it has more inertia. So there's more resistance to changes in motion. So I know you don't encounter any moose or elephants here, but if you're being charged by an elephant or a moose, you want to quickly change your direction. Because if it's moving full speed in a straight line and you quickly turn directions, it's going to be harder for the object to change motion because of its inertia. It's more massive. Awesome. Okay, so what we're going to take a look at, we're going to do a couple stations where we see Newton's first law in everyday life. This unit is a lot more conceptual and less math, at least in the beginning. So we're going to go through a series of stations, which are going to seem like magic, but it's not magic, it's just physics. So you're going to start at the first station here, and you have a water bottle on top of a piece of paper. Your goal is to apply a force to just the paper. So you want to, as quickly as possible, pull the paper out from underneath the bottle. For most of these, you're going to predict what happens first, and then explain what you see. That's station 1. For station 2, we're going to use a car as an example. So this penny is supposed to represent you, the passenger in the car. You're going to put the penny on top of the car, and you're going to increase the height of the books. You're going to measure how far away the penny lands from the front of your vehicle as you increase the height of the frame. Okay, station 3, you have a beaker, a note card, and it says penny, but it's just technically a euro. So you're going to put the note card on top of the beaker. You want to center the euro on top of the note card. You're going to apply a force just to the note card. I don't want to read it for you, so I'm just going to show you what I mean. You apply a force to the note card. Jenny, watch out, it's going to come flying at you. So you're going to flip the note card forward. I was getting afraid, I don't know why. There you go. So you're going to flick it forward and see what happens to the pen. You explain what you see. Last 2 stations are going to occur at this table here, and this table here. There's a tiny URL link. So one's a GIF that you're going to watch. Explain what you see. The other one is a video. will need one computer per group. You need the handout you took off the table. You're gonna get to a station and get started. I'll let you pick your partner. Or I can sign them complete. Then I'm gonna move. Great. Okay, Ryan and Chris, head to station 1. Emily and Jenna, head to station 2. Zoe, Jackson, 3. And then you guys are gonna need to do 3. I'm gonna head to station 4.
Computer might be Armin's still watching.
Sorry.
Thank you.